a few measurement definitions, and let's begin by saying, explaining the concept of sensitivity in measurement. Sensitivity is defined as the amount of change in the output signal from a transducer to a specified change in the input caused by a physical parameter. Clearly, if you're trying to measure something, then you need to be able to detect a change, because we're all about measuring change here. But if the sensitivity is too great, then the measurement becomes subjective to noise and to other external influences. So we need to understand the concept of sensitivity and how to measure sensitivity as part of the transfer function of an instrument itself. So, sorry, I had to make an adjustment here, which I'd not set up properly. That's better. Okay, so we then look at issues such as range and span. And I want to introduce a few concepts here to say that if I draw a scale of an instrument, then clearly I end up by explaining the go to another issue here. I say that the bottom end of the instrument is what we call 0%, and the top end is 100%. Now, this is sometimes said to be the degree of deflection if it's a mechanical instrument, or we can talk about the range and the span. The point is that if we're making a measurement, for example, suppose we will want to make a measurement as to the temperature of the room that we're in, then clearly we don't need a measuring system that measures from absolute 0 to 10 times the temperature of the sun. What we need to do is to be able to look for an instrument that will cover a range that we think we're going to encounter. And so you might suggest that actually if we start at, say, 10 degrees, and I'm talking here of Celsius or degrees Kelvin, then we might want to go to a maximum temperature of, say, 40 degrees. So these are our engineering units. And we need to know what those engineering units are. But when we discuss the range of the instrument in terms of its percentage deflection, then we talk then about normalized range. Because once we've decided what the engineering units represent, we can use the normalized range, for example, 4 to 20 milliamps, or it could be 0.2 to 1 bar pressure. It could be a 1 to 5 volt signal, things like that. What we then need to do is to work out what the sensitivity of the instrument is in terms of the range of a change in degrees for a change in the output or normalized range. You can certainly think of the instrument as having a transfer function, and the input here we specify is, again, let me give you some terminology here. We talk about a measured variable. Sometimes we talk about a process variable, PV, and we talk about the instrument output, and that is in the range 0 to 100%. that could be typically a 4 to 20 milliamp signal, or it could be described in other means. So we've got a lot more to think about here. The sensitivity is the degree of change of the input which causes a change in the output. And so looking at the range and span, then we can clearly adjust the sensitivity by choosing the range and the span according to the measurement that we want to make. So if everyone's happy with that, the span of the instrument, of course, is the and let me put some more terms on here. We have here, down here, we have the lower range value, and we then have here the upper range value. So the span is said to be the upper range value minus the lower range value. Oh dear, I've collided. Sorry about that. Let me just move that over so you can see it. So that's what we define as the span. You also hear this stated in a number of other ways. What I'm trying to do is make you aware that manufacturers, when they quote details about their instruments, what they will do is they will use slightly different terminology. So you may see this referred to as a lower scale value, for example, LSV, and quite rightly you have an upper scale value at the other end. So there are all sorts of names that people use. Again, make sure you understand when you're reading a specification what these details mean. Okay, so there's where we start. Let's have a look now, if everyone's happy with that, let's have a look at the concept of accuracy, which is a very important aspect of any measurement. Accuracy is defined as the amount of error that may occur when measurements are made. And to illustrate this, let me give you the example of suppose you're, being English, you know, archery is one of the things I identify with, and if I was to explain this as an archer, then I would be aiming at the center of the target, which is called the bull. But if I found that my arrows were hitting random places around here, you can see that one of the ways I can correct this issue is to aim down here somewhere. And this concept illustrates that there's a total error, but within that total error there are things like systemic error, or bias, as we sometimes call it. Sometimes it's also called offset. And then there is a difference between what we call random error. Another word for that is precision. So precision is, if you like, the average value because of the randomness of our measurements, whereas repeatability is, if you like, the total excursion encompassing random error or precision, but without systemic accuracy, systemic bias. Because what we can do, as we said, is to change our aim. We can get rid of that bias by aiming somewhere else, or by adjusting, making adjustments somehow within the measurement. So if we then center that element of repeatability over the target, we are improving the quality of the measurement. We're improving the accuracy of the measurement. So another way of looking at accuracy is how precise or correct the measurements are. Precision is, if you like, dealing with the random error that you cannot calibrate out of a system. I think that's a reasonably good explanation of the concept of accuracy. But I'm afraid there's more to it than that. Accuracy versus precision, again, the problem we have is that we can have instruments that range from the precise but inaccurate to the imprecise but accurate. And so this way of explaining that the actual temperature we're trying to measure is there, but what we find is the instrument randomness is creating what we call an envelope. So there's an envelope there which is really expressing the accuracy of the whole thing. If I draw that envelope, then that contains all the deviation that we see. But here we've got something that's precise, it's correct, but it's inaccurate because there is an offset here. This whole measurement is biased upwards on the temperature scale. So again, what we must ask for is how close do we want how close and in what axes do we want the accuracy of the instrument to be? Some of these explanations will become a little more apparent when we start looking at particular types of instruments. So don't worry if this is a little vague to start with, but please look at these explanations more in the manual as you go along. Okay, let's now turn our attention to repeatability. How close is a second measurement to the first measurement under the same operating conditions and the same input? So the idea is that we have an instrument input which is then taken up to a particular level. It's then taken down again. It then goes back up to the level a second time, and what we want to know is how close is this measurement to that measurement. So this is expressing repeatability more specifically. The other phenomenon here is range of operation. Now, an instrument will be able to operate within a defined range, and they will be extremes. So the actual calibration of the instrument could be between two extremes. So the range of operation is effectively the high and low operating limits for a given measurement capability. Whereas when we calibrate an instrument, what we are doing is we are choosing a range or a zero and a span within the range of operation because that's convenient for us in terms of the measurement that we're doing. So then we have a measurement here, and that becomes our, sorry, just having trouble aligning this, that becomes our 0% there. And then this line here represents the 100%. So the range of operation is important. The span of an instrument will have a ratio between the range of operation, and of course that determines the sensitivity of the instrument. So the smaller we can make that span, the greater the sensitivity of the instrument. And of course, as the sensitivity increases, we would expect repeatability to become poorer. So there is a sort of relationship between these. The other issue on the side here of deadband, I just need to explain a little bit about. If there is a movement in the process variable, but the instrument itself cannot see that variation, then this is what we call the deadband of the instrument. Okay, now in some cases that deadband can be reasonably large, a relatively high proportion of the span that we choose on a poor instrument. On a good instrument, deadband is very, very small, perhaps immeasurable. But again, we need to know what that is. At this stage, let me just launch off temporarily into a different realm and ask you, what is the difference between, here it comes, what's the difference between analog and digital? These are terms that we use quite often, quite regularly, but do we really know what they mean? What's the difference? Anyone care to give me a few words of explanation on that? How would you define that difference? Jason says that digital has discrete values in a range. Okay, I think I see what you mean by that. Any other contributions here? This gives me an opportunity to sip a little water while we're thinking. Analog is wired, digital is a frequency signal. Yep, okay, that's a possible thought. Digital takes value from finite sets of values from Colo. Thank you for that. Yeah, I think I see what you mean. I'm just wondering if we're getting any other contributions here. It's funny how when you write something down like this, you then want to clarify it. So that's not an unreasonable thing to do. Let me put this in perspective, or try to do so, and say that here we have a trend screen. Let's suppose that the trend is downwards. So perhaps we're looking at the cooling of something cooling as the temperature gets lower. Here's temperature, and here's time. And so you can see that something is cooling. Again, you see, if we capture a signal at this point in time, we say, at that point in time, what is the value of the signal here? Then we can express that as a pattern of ones and zeros, which takes the form of a digital value. So digital is not really all about on and off as binary, but it's a case of looking at the digital representation of an analog signal. An analog signal is truly infinitely variable, whereas a digital signal has resolution. And it's this resolution that I want to focus on. Let's suppose that the 0 to 100% range of my instrument, my measuring instrument, so the 0 to 100% range has a 12-bit A to D converter on it. So if it's 12 bits, anyone know what the resolution of the measurement is with 12 bits? Anyone help me with that? In other words, how many steps are there between the 0 and the 100% if I'm representing this signal digitally? Well, I can see typing. Anyone going to help me with a figure here? So, no, you've actually chosen 8 bits. You've actually chosen 8 bits. 12 bits, would you believe, is 4096. And that means that for each increment, it represents 1 in 4096 parts, or 1/4096th of the range of the instrument. So if I was to amplify a small section of this, and I'm going to exaggerate this for the effect, then as you might expect, what you find is that your signal comes down in steps. And the steps, the size of those steps there represent 1/4096th of the range of the instrument. And I say that because if the analog signal moves within that resolution, that is in fact a deadband which is present by virtue of the fact that we have digitized an analog signal that's been captured. So again, sometimes we can artificially change that deadband, but I want to point out that there is an inherent resolution in a digital signal, and that resolution equates to a very, very small deadband. So 2 more terms defined there, I hope.